Hello everyone, welcome to my group theory lecture. In this lecture we study examples of groups. For starter, the set of all integers with addition, the set of all rational numbers with addition, the set of all real numbers with addition, and the set of all complex numbers with addition are all abelian groups of infinite order. Do you remember we talked about the order? Order means the number of elements, okay, of the given group. So it is called order, right? As we know, of course, each set, the set of all integers, set of all rational numbers, and the set of all real numbers, the set of all complex numbers, they all have like infinity, infinitely many, the numbers, right? So uh, they all have infinite order. Okay, next example, the set of all rational numbers. Uh, this notation is a set minus, okay? So, so the zero excluded, what that means is, so Q minus this singleton set having only zero, that's, the set of all rational numbers with, the zero excluded with multiplication is an abelian group of, again, infinite order. Now here we have a new notation, which is R plus, right? This R plus denotes the set of all positive real numbers. And this is it. So with multiplication, this is an abelian group of infinite order. Okay, next example is, unimportant. I mean, they are all important examples, but particularly important. Um, so E sub n, we are going to define E sub n to be the following set. So that's EXP. That's notation. In case you are not familiar, that's actually, the same thing as E, right? So, the uh, exp of 2k pi I over n, what that means is the same thing as, I think I better write, okay? So I'm gonna go to my notepad. So this is just a, notation. So the one I wrote there, exp, okay? Exp of 2k pi I over n. So 2k pi over 2k pi over n I, right? That is the same thing as, you know, the number e, right? Okay, so e to the same thing as writing e to the 2k pi over n I. So when this exponent part is, the complicated, okay, complicated, then we use this notation instead, right? Otherwise, well, difficult to write, also difficult to read. So this is actually better notation, right? Okay, going back to, now we are going back to my lecture slide, okay? So E sub n is a set of those guys, e to the 2k pi over ni, and here k runs from 0, 1, 2, all the way to n minus 1. So E sub n has what, how many elements? There are n elements, right? Okay. So what are they? So E sub n is set of, these n elements. These are, in fact, the nth roots of unity. What does that mean? That means the zeros of the equation, z to the power n equals 1. So these are the solutions, okay? There are n solutions of this equation, z sub n equals 1, and those are the, those are the n solutions of this equation. E sub n forms an abelian group of order n with multiplication. Okay, so I forgot to mention that, but when you talk about a group, it is very important to specify what operation is involved, right? So in this case, the E sub n forms an abelian group of order n with complex multiplication, because these are all complex numbers, so complex multiplication. Okay, it is generated by a single element, e to the 2 pi I over n, and such a group is called a cyclic group. So what we mean by actually generated by a single element. So starting from this element here, by successively applying the operation, okay, you can actually, produce all the elements there. So that's what we mean by the group is generated by this single element. Okay, in this case also, e to the 2 pi I over n is called a generator of this group. And so we will talk a lot about the cyclic groups later on. Okay, but again, such a group is called a cyclic group. A group generated by a single element. That's a cyclic group. Okay, so let's actually take a look at one particular case of this, the E sub n. So, so let us consider, so this is notation, okay, so this is it. Notation. Okay, and let us consider this equation here. G to the power 6 equals 1. So let's solve this equation. You probably have done this, in case, for example, like, if you have taken like functions of one complex variable course, okay, that's, very beginning, that's one of the things, we usually do. But in case, you are not familiar, let's talk about this. Okay, so how do we solve this type of equation? It is convenient to use, the polar form, the excuse me, the polar form of a complex number. So let a polar form means that, z equals r times e to the I theta. Okay, this is the polar form. Of a complex number Z. Okay, so let's use this. Then, so we are going to replace Z by this polar form, and so we obtain, what is that? R times e to the I theta to the power 6 equals 1. And this guy is what? Same thing as R to the power 6 e to the 6 I theta. Okay? Oh, here, R is, of course, what is that? The uh, the length of this complex number Z, right? Uh, I might actually better tell you a little more explanation. Uh, well, in case you are not familiar with it, not very familiar with it, the complex number. So let's say this is complex number Z. Okay, complex number Z, right? So in general, like the complex number is written by like the A plus IB. So here A is the real part of this complex number Z. B is the imaginary part of complex number Z. What I mean by is that the projection of this line here, right, onto the x-axis, that's where you get the real part, that's A, and the projection of Z onto y-axis, you get the imaginary part. All right, so this is one way you can write it down. All right, and another way you can describe is polar form. So this angle, there is unique angle, right, for each given complex number. So let's call it theta. Okay, theta is of course measured from the x-axis, right, counterclockwise. Okay, that's the convention. So the length of this C, R, so let's call it R, all right? So R is found to be by Pythagorean law, right? That's easy. So everybody knows that. That's the square root of A squared plus B squared, right? And also, say when the R equals 1, any the what is the complex number with the length 1, that's actually point on the unit circle. Okay, that unit circle, the case. I don't know if I can draw a circle also. Oh yeah, there is one. All right, so the here's another So here's another one. Oh, so that's not the. So I better draw circle first, and then put axis there. Okay. I think this is okay. Uh, yeah, a little bit off, but that's okay. Yeah, I think that's good enough. So let us assume that, that this is like a unit circle, right? So circle with radius 1, circle with radius 1, okay? In fact, also we will, it can be shown that, in fact, A plus IB, right? This is also identified with the ordered pair. So in complex plane, this point here is written by A plus IB, but in R2, okay, it is the point given by this ordered pair AB, okay, in Cartesian coordinate. To be more the specific, right? So in fact, the topologically speaking, the set of the complex plane is the same as the set of all complex numbers is topologically equivalent to the R2, but that's you don't have to worry about those things right now. So what I'm saying is that in this case, any point on the unit circle, right? So here's there's a corresponding angle, unique angle, theta. So, this point here is what? Exactly cosine theta, as you have learned in trigonometry and sine theta. Sine theta. Okay, so first the coordinate is given by cosine theta, sine theta. And the point cosine theta, sine theta is in fact the same as, in terms of complex numbers, cosine theta plus I sine theta. And that is what? Same as e to the I theta. Okay, so this part here, right? E to the I theta equals cosine theta plus I sine theta. That's called, this can be proven, for instance, using, the power series, okay? Power series representation of Maclaurin series representation of cosine theta and sine theta. You can actually easily show this. But anyway, this is called what? Euler's formula. Many pronounce this name, the Euler, Euler, right? Especially like if you are Americans, okay, but the Euler, that's uh, close to the correct pronunciation, right? So Euler was an Austrian. I don't know actually. That's the a little bit controversial, right? The Austrians, they claim that Euler was Austrian, and Russians claim that Euler was Russian because he was living in Saint Petersburg. Okay, Saint Petersburg. Uh, I'm sorry, that's incorrect. Not the Saint Petersburg. The today's Kaliningrad. Okay, the exclave of the Russia. The old name is Königsberg. Right. Okay, so I remember. Uh, so all the time there was. I mean, this is not important, but it's fun to know. Okay, like a little bit of history. I'm not a history buff. I mean, mathematical or non-mathematical, I'm not a buff, but it's always good to know to some like a historical fact. So you know what? Before I regret saying something wrong, I'm gonna quickly check if I got it correct. Okay, yeah, I misspelled it. That's umlaut. Okay, right? You see a lot in German. So O with the two dots, Königsberg. Actually, more likely Königsberg, right? Königsberg, right? Uh, and that's modern day Kaliningrad in Russia. Right. So if I remember correctly, I think it is Kaliningrad, originally Königsberg, the part of Austria. After the Second World War, uh, I think the U.S. President Roosevelt, gave this the city to Russia. Okay, Russia was a very important ally, during the Second World War, and so I think to appreciate like their contribution, the Roosevelt, gave this city to Russia. Now it became, the an exclave of the Russia. Uh, and the name is Kaliningrad. So anyway, that's the reason why, like it's controversial, like But anyway, what's important is that this is called the Euler's formula. All right, so let's get back to our business. Okay, I got distracted. Okay, so that's how we get this, right? So the polar form. So for any complex number whose length is r, okay, r, of course, all you have to do is to represent it in polar form, z equals, e to the I theta. Any unit any unit, the complex number. So complex number with unit length, it is given by e to the I theta, as you can see. Okay, and so by comparing these two, so right hand side we have only like a real number, right? So what that means is this implies that r to the 6 equals 1 and e to the 6I theta that equals 1 as well. Okay, so r to the 6 equals 1, r is a real number, of course. So in that case, we have only one real solution. So r equals 1. And from, 6I theta, e to 6I theta, so that's same as cosine 6I theta plus, oh, sorry, that's not it. Cosine 6 theta plus by Euler's formula, I times sine 6 theta equals 1. Okay, so here by comparing real part and imaginary part, right hand side is a real number, so there is no complex, imaginary part, right? What that means is cosine 6 theta equals 1, so real part has to coincide, and also when we say two complex numbers are the same, means the real parts are the same and corresponding imaginary parts are the same. So sine 6 theta has to be 0. Okay, so for right, so for 6 theta greater than or equal to 0, less than 2 theta, less than 2 pi. Okay, 2 pi, that happens when 6 pi equals so this is 1 and this is the 0, right? That happens when this is pi over 2, right? That's no, I'm sorry, not the yeah, it looks like I'm still not fully awake. Okay, so no, cosine is 1, sine is 0. That's what, when theta equals, this angle equals 0, right? So this angle equals 0, so 0 case, right? Like, cosine 0 equals 1, right? Between when, I better write down. So here, if 6 theta, right, 6 theta is greater than or equal to 0, less than 2 pi. So there is only one angle that satisfies these two equations, okay, which is 6 theta equals 0. However, that's just one possibility, right? Okay, and the cosine and sine, these are periodic functions. And what's the period? They both have a same period, 2 pi. So after 2 pi, 1 rotation, 2 rotations, the 4 pi, 3 rotations, 6 pi, and so on and so forth, you still end up getting the same value. So if you want to count all the, the possible solutions, right? Okay, you have to write it. So if you want to include it, count all the solutions, right? All possible solutions, you have to include plus 2k okay, 2k pi. And here, k, k is an integer, so 0, 1, 2, 3, 4, 5, and so on and so forth, okay? Right. So theta is going to be, if you divide each side by 6, 2k pi over 6. So we found it, and here in this case, k runs from, so how many are there, right? How many are there really? So k runs from 0, 1, 2, 3, 4, 5. Actually, this is it. So what happens when k equals 6? So when k equals 6, you get 2 pi. So it's actually the same as when k equals 0. So it keeps rotating, right? So really, these are only six distinct, solutions. So k equals from 0 to 5. They give six distinct solutions of this solution, right? So we found all the solutions now, and we are going to write that as E6, E sub 6. So that's going to be e to the 2k pi over 6 I, such that k runs from 0, 1, 2, so from 0 to all the way to 5. So 0, 1, 2, 3, 4, 5. So there are 6 distinct solutions. Okay? In fact, excuse me, if you plot this point, you get, a beautiful geometry, the structure. Before, so we talk about, yeah, right. So you can actually easily plot those points. Okay. So the what is that? The first one is so that is what the length one, right? The complex number. So we have when k equals 0. So let's write those down. So k equals 0, we have 1. So we have so this equals 1 e to the, when k equals 1, 2 pi over 6, that's pi thirds I. And when k equals 2, that's going to be e to the 2 pi thirds I. And k equals 3, that's going to be e to the pi I. And k equals 4, that's going to be e to the 4 pi thirds I. And then lastly, e to the, the 5 pi thirds I. So there are, so by looking at these angles, you can easily plot those points, right? Pi thirds, that's 60, right? So where your radial component is located, at the angle, the pi thirds is 60 degrees, and so on and so forth. So if you, so let's go to my slides. In fact, we get this beautiful picture, so the first one, that's 1, right? This is where the angle is 2 pi over 6, pi thirds, okay, and so on and so forth. All right, so let's move on. So in fact, this guy here, e to the pi thirds, e to the pi thirds I, that's the generator. And this guy, in fact, produce all other, the elements in this cyclic group. Okay, actually we talked about this definition before, but as a reminder, again, a group G is said to be a finite group if it has a finite number of elements. The number of elements in G is called the order of G. Again, we talked about that. And it is denoted by, this absolute value notation, okay? But that's not absolute value here, that's order of G. Okay, the number of elements in the group G. I actually introduced some time ago, right? When I talked about this, not just this also, another like a common notation is ORD, okay? ORD of G, but we are not going to use that notation, so I'm not repeating here, okay? This is the notation we are going to use for the order. Okay, so here's another important example. Z sub n, this is actually a very important example. Z sub n, this is a set of the following n elements, 0, 1, 2, all the way to n minus 1. What is this? Z sub n is the set of all possible remainders when an integer is divided by 2. Okay, when an integer is divided by no, that's not right. That's not right. I'm sorry, this is typo. No, that's it. That's the definition of Z2, which is showing, in the table below. No, it should be n. Okay, I'm sorry. So Z sub n. Let me repeat that. Z sub n. Z sub n is the set of all possible remainders when an integer is divided by n. So in that case, as you know from the division algorithm, the possible remainders are from 0, 1, 2, all the way to n minus 1. Those n numbers are the only possible remainders when an integer is divided by n. Okay? And the addition on Z sub n is defined naturally as follows. So here, I'm using the simple case Z2. So Z2 case, what is that? That's the set of all possible remainders when an integer is divided by 2. Okay, so the only possible remainders are 0 and 1. Okay? All right? So Z2 has only 2 elements, 0 and 1. So 0 plus 0, of course 0. 0 plus 1 equals 1. 1 plus 0 equals 1. And the next one, 1 plus 1, this is where an interesting thing happens. 1 plus 1 equals, of course, as an integer summation, that's 2, right? But remember, Z2 is the set of all possible the remainders when an integer is divided by 2. So it's got only 2 elements, 0 and 1. Okay? So 2, when you divide 2 by 2, what's the remainder? That's 0. So as a remainder, it is 0. So 1 plus 1 equals 0. So in fact, Z2 is a number system where 1 plus 1 equals not 2, but 1 plus 1 equals 0. Okay? So, 1 plus 1 equals 2 is not. It's not like, absolute truth, right? There is a number system where 1 plus 1 equals 0. Okay? So you may find it interesting. So here's another example, Z3. So we are looking at the, addition table of Z3. So Z sub 3 is, again, the set of all possible remainders when an integer is divided by 3. So, there are only 3 possibilities. Excuse me. So, remainder can be 0, 1, and 2. So those are only 3 possibilities. So Z sub 3 has 3 elements, 0 and 1. I'm sorry, 0, 1, 2. 0, 1, 2, only 3 elements. Okay? So let's take a look at this multiplication table. So 0 plus 0, 0, 0 plus 1 equals 1, 0 plus 2 equals 2. Not so much interesting, okay? And 1 plus 0 equals 1, 1 plus 1 equals 2, 1 plus 2 equals 3, okay? 3, when 3 is divided by 3, remainder equals 0, so that's 0. 1 plus 2 equals 0 here in this Z3. And 2 plus 0 equals 0, 2 plus 1 equals 3, right? 2 plus 1, 2 plus 0 equals 0, 2 plus 1 equals 3. Something is not right, okay? I'm sorry. Still I'm not fully awake. It's kind of, early in the morning. I woke up actually very early in the morning. No, what the heck I'm talking about? 2 plus 0 equals 2. This table is so wrong, okay? So this third row is entirely wrong, okay? Probably when I was making this also, I think, maybe I was sleeping or something, but, yeah. Yeah, I don't know, I was repeating like some nonsense. So, I got mixed up with multiplication and, addition. No, sorry about that. Anyway, yeah, I'm correcting it. 2 plus 0 equals 2, right? 2 plus 0 equals 2. So this has to be 2. And 2 plus 1 equals 3. So when you divide the 3 by 3, that's the remainder equals 0. So this has to be 2, 0, and 2 plus 2 equals 4. 2 plus 2 equals 4. So when you divide 4 by 3, remainder equals 1. So this has to be 1. So third row, right, after this 2, the numbers should be 2, 0, 1. 2, 0, 1. Okay, so I'm going to correct this, right? I'm going to correct this after, I finish recording this lecture. Sorry about the confusion, okay? So moving on. In general, Z sub n with addition is an abelian group of order n. Okay, that's an abelian group. So, the operation is commutative. And E sub n and C sub n are the same group, So you might say, what the heck are you talking about? They look very different, right? But here, same means they are. Remember, some time ago, I talked about in the introduction, I talked about what we mean by two groups are same in group theory. Okay, in group theory, we say two groups are the same by they are being isomorphic. Okay, so one group is isomorphic to, the other group. In that case, we actually say two groups are the same, right? So I think, you might have forgotten that. So, why actually do I show you this, right? So remember isomorphism, right? So yeah, actually I gotta get to my notepad. Okay, so this is an example. This is an example. Okay, so here I don't know what to call it. Let's call it theorem, yeah, theorem. So uh, C7 is isomorphic, isomorphic to E sub n, okay, E sub n. So let's prove this. For proof, I'm gonna use a different color. So here's proof. So to show that C sub n is isomorphic to E sub n, we gotta come up with a map, all right, an isomorphism. Okay, so we are going to define a map phi, okay, a map phi from C sub n to E sub n, right, by actually pretty natural way, okay, natural way. Uh, oh, by the way, I think I need to specify this, although you know that, right? But Z sub n is additive group, so operation is positive, and E sub n, as I mentioned earlier, the operation is complex multiplication, okay? And here, phi of, the phi of k, phi of k equals e to the 2k pi over n I. Here, k equals 0, 1, 2, all the way to n minus 1. All right. So what do we have to show? So we show that phi is on isomorphism, on isomorphism. Oh, by the way, this is a Greek letter, right? Greek letter. So, this phi is usually written as, the following, like PHI. So, a lot of folks, including like, the colleagues and students, they pronounce it phi, and that's understandable. But, the original Greek pronunciation. That's not phi, that's phi. So that's why I keep saying phi. Okay, I always try to the pronounce like certain letters, words, right? Uh, close to close to the way the folks pronounce it, right, in their own language. So that's actually also my way of like respecting, the each individual culture. So I don't like that. So yeah, I mean that's not actually important, but I'm just telling you. So why I'm pronouncing it, fee. Although a lot of folks, especially the Americans, to pronounce this fee. Anyway, so we're gonna show the following. So first one is in order for this phi to be an isomorphism, it has to be an one-to-one and one-to, right? So phi, first we have to show that phi is, of course, well-defined, okay, well-defined, but phi is, right, so well-defined. What do you mean by well-defined? It is a function, okay, it is function, but that's clear. So I'm not gonna do that, okay, it is clear. So basically, what I mean by well-defined is what? If K equals L, right? K equals L, then, e to the 2K pi over N, I equals e to the 2L pi over N, I. Okay, so that's clear. Both K and L are one of those things, right? Okay, so 2 phi is 1-to-1. So we have to show that it is 1-to-1. Or another word, in other words, it is injective, right? Injective. Injective. So what does that mean? If what that means is e to the 2k pi over n I equals e to the 2l pi over n I. That implies k equals L, right? That's what we want to show. I mean, this is where we are heading at. So delete this, okay? So this means that something is missing, right? I deleted that. So this implies that using Euler's formula, cosine theta, no, not the cosine theta. Oh, actually, I didn't realize, time has gone already, yeah, I always, I have a problem, I always try to make my recording, no more than 30 minutes, but then when I talk about math, maybe I get excited and then I just forgot to check time and it's already like close to 1 hour. So I guess, I gotta finish it and then that I'm gonna stop it, okay? Finish this theorem and then I'll stop, actually, the folks usually, including me, it's difficult to stay focused, you know, uh, you know, to stay focused on lectures or speeches, for more than 1 hour, right? So Anyway, cosine, what that means, left hand side is cosine 2k pi over n plus I times sine of 2k pi over n, and that equals right hand side using Euler's formula, that's cosine 2l pi over n plus I times sine 2 L pi over n. Okay, and so these two complex numbers being the same means that their corresponding real parts are the same and their corresponding imaginary parts are the same. So you know what that means is, so this implies that cosine 2k pi over n equals cosine 2l pi. You know what? I just realized that actually there is an easier way to do this. Sorry about that. Let me go back. Okay, I'm gonna erase this. Sorry. Yeah. I like easy. I like easy and simple. Okay. So what this means is, if you multiply each side by, you know, the e to the negative. Okay. So multiply each side by negative e to the negative 2l pi over n times I. And then what do you get? You get, so this implies that e to the 2 times, in the case, k minus l pi over n I, that is going to be 1. Okay, so this implies, using Euler's formula, that's cosine 2 times k minus l over n pi plus I times sine 2 times k minus l over n pi, that equals 1. Okay, that equals 1. So right hand side, you know, is a real number. So imaginary part equals 0. So by comparing these two complex numbers, right, we get the following thing. I'm out of space, so I'm going to move to next page. Okay. So this implies just give me a moment, okay? I got to take my morning medication. Sorry, I'm back. So what this means is that a cosine, by comparing you know, the real part and imaginary part, we get cosine of 2 times k minus l pi over n, that equals 1, and sine of 2 times k minus l over n pi equals 0. Okay, so for this whole angle, right, 2 times k minus L over n pi. So when this is greater than or equal to 0, less than 2 pi, there is a unique angle, right, which satisfies this equation. What is that? When this angle equals 0. Okay, cosine 0 equals 1, sine 0 equals 0. That's the only, the angle, right, satisfying these two equations. So with this condition, right, we have 2 times k minus L over n pi equals 0, which means that k has to be same as L. Okay, so we just showed that the phi is 1 to 1. And clearly, phi is onto, so that's easy. That's or, surjective, right? That's another name. Okay, because for any member E sub n, okay, right? For many, so for any e to the 2k pi over n I in E sub n, this k runs only from 0 to n minus 1, so this k belongs to z sub n, and phi of k equals e to the 2k pi over n I. So it is onto, right? So from the 1 through 3, right, that tells us that phi is a bijective function, right? A bijective function. All right, and so there's one last thing we have to show, right? We have to show that's what for phi preserves phi preserves the operation. Okay, operation preserves the operation. And what we mean by preserving the operation, we talked about that before. In other words, we have to show that phi of, so Z sub n is an additive group, right? So K plus L, phi of K plus L is same as phi of K times phi of L, right? So phi of K, phi of L, these are the members of E sub n, which has the operation complex multiplication, right? So whenever phi satisfies this condition, we say it, the map preserves the operation, right? Well, basically, its meaning, all right, what it means is that, the phi carries over the same, the group structure, okay? Phi carries over the same group structure. So that's why it is important. So that way we can say that two groups are the same. Because when two groups are the same, they must have also same group structure. Same group structure means the same operations, right? Same operations. Okay, so same operations means that, operations are different, right? one side, one side has addition, the other side has multiplication, but the way they operate, are the same. They are the same. All right, so let's show this. So we started from phi of k plus l, k plus l. So that's e to the 2 times k plus l over n pi I, right? So that's same as e to the 2k pi over n I times e to the 2l pi over n I, and the first guy is phi of k times this guy here is phi of l. So we are done. Okay, so this actually completes the proof. So I'm gonna end it with the, I think I mentioned this, right? This is called the Halmos notation. Okay, named after the mathematician Paul Halmos. All right, folks. I think we gotta stop and take a break. Okay, so I'll come back. We'll continue our discussion in my next lecture. Thank you.